हेलो स्टूडेंट्स, नमस्कार सभी बच्चों। एक सिंपल सा स्टेटमेंट ये तीसरी बार लिखा जा रहा है। मैग्नेटिक फील्ड ड्यू टू अ करंट कैरिंग कंडक्टर एंड स्ट्रेट कंडक्टर। ऐसा हम बार बार ऐसा नहीं चल रहा है, बट हियर इट इज स्लाइटली डिफरेंट बिकॉज हियर इज द मैग्नेटिक फील्ड इनसाइड द कंडक्टर, मीन्स इन द इंटीरियर of conductor. And here word thick is written. Actually we didn't require this thing, but for reinforcement I have given this thing, magnetic field inside the thick conductor. Thick means having appreciable cross section. Okay, so inside the conductor, if you you observe the cross section, magnetic field will be different in different parts. Okay, we have to find out variation of magnetic field inside the conductor, and naturally we will assume this conductor is solid, it is filled absolutely, there is no vacancy or vacant region. Okay, each part is filled with material and conducting material. So here figure is showing a uniform conductor. It has, in whole length it has cross section A, and this is uniform cross section. Suppose this conductor is carrying current, and current is also uniformly distributed in the whole cross section. Means in the cross section, per unit area flow of charge per second is same. Okay, think about this sentence. Per unit time, per unit area, charge passed is same in its whole cross section. Okay, जैसे सेंटर में आप इमेजिन करें, बॉर्डर के पास इमेजिन करें, लेकिन है क्या है, क्रॉस सेक्शन के हर पार्ट में पर यूनिट एरिया सेम चार्ज फ्लो कर रहे हैं हर सेकेंड में, मीन्स हर पार्ट में करंट का डिस्ट्रीब्यूशन यूनिफॉर्म है. तो क्रॉस सेक्शन क्या है, ये पार्ट आप ये इमेजिन कर सकते हैं कि ये पार्ट यहाँ, ये पार्ट यहाँ कहीं पर भी क्रॉस सेक्शन में कोई पार्ट हो सकता है. सो टोटल करंट आई डिस्ट्रीब्यूटेड इन द होल पार्ट. ओके, एंड सो पर एरिया करंट इज हाउ मच, पर एरिया करंट इज I is total current is I, then per unit area current is I upon area, cross section area. So suppose this is cross section A and this radius of conductor is R, and here cross section is A. Obviously if cross section is circular, then certainly it will be pi R square. Okay, and I have to find out magnetic field on the axis of conductor. This is axis. Okay, this is axis of conductor, this is surface of conductor on both sides, and this is outside it. So we will test the magnetic field, in the interior, on the axis, outside the conductor. And current, remember it, current is distributed uniformly in its whole cross section. So let us assume, so cross section of conductor is A, and this is pi R square. Radius of conductor, here radius of conductor is R, and we are assuming the conductor is of circular cross section, and here, okay, so, and current distributed. Okay, suppose current flowing through a conductor, distributed uniformly inside, uniformly in its cross section. In its cross section. Okay. So now point area. Okay, point area, current point area of cross section is how much? Then current per unit area of cross section per area of cross section is how much? This is here I, total current I upon pi r square. Okay. So here cross section is circular. तो अभी देखिए, अगर हमें किसी इंटीरियर पॉइंट पर मैग्नेटिक फील्ड पता करना है, मान लेते हैं ये पॉइंट क्या है, ये पॉइंट P1 है. ओके, या एक पॉइंट यहां इमेजिन कर सकते हैं, एक पॉइंट यहां पर इमेजिन कर सकते हैं P1, यहां पर P2. ओके, यहां एक पॉइंट इमेजिन कर सकते हैं P3 and outside this P4. So we can imagine these points. This is on the axis, this is P2 and this point of the surface is P3. So first of all we will go to point this P2. ये अभी क्या है, इंटीरियर में है, करंट का डिस्ट्रीब्यूशन एक जैसा है. क्या करेंगे, एम्पीयर लॉ का यूज करेंगे, और एम्पीयर लॉ का यूज करेंगे. यहाँ पर करने के लिए क्या होता है, हमें एम्पेरियन लूप चूज करना पड़ता है. एम्पेरियन लूप जो यहाँ पर फ्लो है और जो सिमेट्री है उसके अकॉर्डिंग हम एम्पेरियन लूप सर्कुलर ही लेंगे तो अच्छा है. और ये एम्पेरियन लूप, एक बात और पहले से बता दिया, हर हाल में एम्पेरियन लूप कहाँ से पास होना चाहिए, हर हाल में एम्पेरियन लूप उस पॉइंट से पास होना चाहिए जिस पर हमको मैग्नेटिक फील्ड फाइंड आउट करना है. सो अभी अपना इंटरेस्ट कहाँ है, पॉइंट P2. सो वी विल assume an amperian loop, a circular amperian loop passing through point P2, and which will be symmetric to the axis of conductor, and its plane will be perpendicular to the axis of conductor. So here we are taking, this is amperian. This is amperian loop, and so total current here, you can imagine current is passing, current I is passing through the whole cross section. Here current is passing through the whole cross section. So uniform distribution of flowing charges is there in the whole cross section. Okay, here also charges will be flowing here, and this. So this is flow of charges. Some charges are passing through this bonding. There are some flow charges are inside there and some are outside. So here charges are flowing. Total current will be corresponding to these charges. Okay, so we are interested about enclosed current. What current is enclosed inside the boundary or inside the amperian loop assumed. So this is not all current. This is not total current. Some current is here, some current is here, some charges are passing, they are flowing outside the boundary. That definitely current will be some fraction of total current. Means current enclosed by the boundary or amperian loop will be some fraction of total current. And suppose the distance is r. This distance is small r. Distance of point P2 is smaller from the axis of conductor. Okay. First, let us find out magnetic field at the interior point P2 at the interior point P2, and this point is nothing but what? It is at the r distance from the axis, which is at the distance r from the axis of conductor, from the axis of conductor. Axis of conductor. And now assume a circular amperian loop passing through point P2. Now assume a circular amperian loop passing through the point P2 and symmetric to the axis, and symmetric to the axis of conductor. Then current enclosed by this here current enclosed by this amperian loop. Then current enclosed by some amperian loop current enclosed by some amperian loop, I equals I into, or you can say per unit area of cross-section current, it is pi r square, and this will be pi r square. R1 radius of this amperian loop, small r, and this amperian loop is passing through point P2. And here, so pi will get cancelled, I into r square divided by capital R square. So I is total current, this is constant for the conductor, or this is constant for the given setup, and I is current enclosed by this amperian loop. I is total current, and this current is constant for the given arrangement. Now see here, for the field at P2, let us apply Ampere sector law. Okay. So let us apply Ampere sector law. Let us apply Ampere's circuital law. Okay. For the amperian loop here. log for the amperian loop. Okay, so integration B dot dl equals mu naught I, and you can imagine here charges are flowing in a forward direction, particles are flowing in a forward direction. Certainly all charges are flowing in a forward direction. Certainly magnetic field will be according to right hand thumb rule, means current is in a forward direction, and here magnetic field will be according to this direction. It is along this direction. So here magnetic field lines will be circular again. Magnetic field lines will be circular, and for the circular lines here, and as per symmetry tells here, boundary element of this amperian loop will be always perpendicular to the direction of field everywhere. So as the symmetry tells, okay, the magnetic field, okay, magnetic field lines will also be symmetric to the axis. Lines will also be symmetric to the axis, and symmetric to the axis and will be circular, That is everywhere on the boundary of this amperian loop. That is everywhere on the boundary of amperian loop. Okay, magnetic will be parallel to boundary element. Okay. So Miss B is parallel to DL, and B is constant also, and magnitude of B is constant. Magnitude of B is constant. So we have B dot dl equals B dl and B into dl. Here cos B is parallel dl, then cos 0 will be 1, and B is constant also, B dot dl. This implies that B integration dl equals mu naught, and this IE, this is what IR squared divided by capital R squared. and so dl, these all dl when they are integrated they will give circumference of amperian loop. So b into 2 pi r or b into 2 pi small r equals mu naught I r square divided by r square. So we have or b equals mu naught divided by 2 pi I into r divided by r square. And see here, this whole thing is constant. For the given setup, this thing is constant. R is what? This is position of point P2 with respect to axis of conductor. So this P may be here or here or here or on the axis. Okay, you are free to take P anywhere in the interior. So this is interior point. So R will be different for different points, but all interior points this is constant. Okay. For all interior points, mu naught upon 2 pi, mu naught upon 2 pi I upon r square is constant, here. So we have, so see this thing here, B, this is a result, okay. So B is directly proportional to R. So B is, this implies that B directly proportional to R. Means as you go away from the axis, field increases. It is proportional to B or proportional to R. Okay. और so R यहाँ मैक्स अगर यहाँ पर पहुँचते हैं आप सरफेस पर तो क्या हो जाएगा, इंटीरियर मैग्नेटिक फील्ड क्या होगा, मैक्सिमम, इंटीरियर मैग्नेटिक फील्ड मैक्सिमम होगा. ओके. So P3 and P1 we can imagine on the axis here, then on the axis R small r is 0, small r 0, this means interior field is 0. So interior on the axis magnetic field is 0 everywhere. So this is very important here and very good result. So R equal to R inside only. Okay. So first case here on the axis means at P1 is here, it is taken. Okay, for interior point P1, interior point P1 R is 0. So clearly it indicates, this indicates what? On the axis might be 0. B is 0 on the axis of conductor, of current carrying conductor. Okay. So this is it. And certainly on the surface, so at point P3, for surface point means P3, the small r is equal to capital R. is radius of conductor. Small r equal to capital R, and definitely this is a result for then B surface, and B surface got mu naught upon 2 pi I r upon r square. So B surface, and this is equal to mu naught upon 2 pi I divided by r. So again you are familiar with this result. Okay, mu naught upon 2 pi I by r. Now take the point P outside the conductor. यहाँ पर क्या हो सकता है, आप खुद इमेजिन कर सकते हैं कि यहां से अगर आप एम्पीरियन लूप इमेजिन कर लीजिए तो ये टोटल करंट कितना गोस करेगा भाई। आप चाहे यहां ये पॉइंट आप लीजिए, चाहे और कोई और पॉइंट लीजिए, कहीं पर भी इट विल इनक्लोज टोटल करंट। तो इनक्लोज करंट अब बढ़ने वाली नहीं है। इनक्लोज करंट इंक्रीज कहां तक होती है, जब आप सरफेस की ओर बढ़ते हैं। जब सरफेस की ओर बढ़ते हैं तो एम्पीरियन लूप से जो इनक्लोज पॉइंट है, इनक्लोज करंट है, एम्पीरियन लूप में जो इनक्लोज करंट है वो करंट इंक्रीज होती है फ्रॉम एक्सिस टू सरफेस। अगर एम्पीरियन लूप बड़ा होता जाएगा तो इनक्लोज करंट क्या जाएगी, इंक्रीज होती जाएगी। लेकिन इसके बाहर अगर आप कोई पॉइंट लेते हैं और सिमेट्रिक सर्कुलर एम्पीरियन लूप अगर आप इमेजिन करते हैं तो करंट उतनी ही रहेगी, इनक्लोज करंट, चाहे आप कितना भी बड़ा आप ले लें। बस बढ़ने वाला क्या है, रेडियस। किसका रेडियस बढ़ेगा, एम्पीरियन लूप का रेडियस बढ़ेगा। तो एम्पीरियन लूप का रेडियस बढ़ेगा तो रिजल्ट पर फर्क पड़ेगा। तो देखते हैं क्या होगा। तो आइए, तो ये रिजल्ट है। अभी आउटसाइड पॉइंट, तो टू एन आउटसाइड पॉइंट। ओके, so let us see. So third basic, to an outside point means P4, so here current, enclosed current will not vary with the radius of amperian loop. Okay, the enclosed current will not vary with radius of amperian loop, or you can say position of point, क्योंकि आप उस पॉइंट से जो उस पॉइंट से ही तो पास हो रहा है एम्पीरियन लूप, तो एम्पीरियन लूप की रेडियस किस पर डिपेंड करेगी, पोजीशन ऑफ पॉइंट पर। और पॉइंट क्या है, कहीं बाहर बहुत दूर लेते हैं तो एम्पीरियन लूप भी क्या होगा, बड़ा एम्पीरियन लूप। दैट इज enclosed current will remain same। enclosed current क्या होगा, उतना ही रहेगा, चेंज नहीं होगा। I तब क्या होना चाहिए, then applying Ampere second law, AB dot dl mu naught I. So like earlier suppositions, we have here also according to symmetry, according to symmetry. According to symmetry, okay, B is parallel to DL everywhere, and magnitude of B is constant. Magnitude of B is constant. Magnitude of B is constant on the amperian. So you can write BdL mu naught equals mu naught I, or B equals B into 2 pi r, and this is equal to mu naught I, or B equals mu naught divided by 2 pi I divided by R. Okay. So here in this case, with increasing R, B will decrease. Okay, because there is no change in current. Earlier, in the case of point P2, in the case of interior point, this current, enclosed current was increasing with increase in R. Okay, but outside point के लिए क्या है? वहाँ पर R की वैल्यू बढ़ती जाएगी, फिर भी करंट उतनी ही रहेगी, क्योंकि कंडक्टर कहाँ लग रहा है? कंडक्टर यहीं लग रहा है, और करंट उसी कंडक्टर को हो रहा है. Here B is also proportional to 1. So these are important results about this conductor or its interior field and outside field also. So let us see the graph here. Let us erase this part, and I want to draw a graph related to this. And suppose okay, so I am drawing graph related to this axis. Okay, this origin is lying on the axis, and this is distance from the axis. R is distance from the axis. Okay, so let us see. This distance represents I equals capital R, means this position is corresponding to surface of the conductor, or position of surface of the conductor with respect to axis. So as we go away from the axis, this magnetic field increases. Okay, magnetic field increases linearly, because inside the conductor B is proportional to R, and outside it is inversely proportional to 1. So here B is increasing linearly inside the conductor, but outside here it is decreasing. Outside it is decreasing. So here B is directly proportional to R, but outside B is inversely proportional to. Okay, so this is the result. You can compare. To compare this thing, I have given graph. It is not necessary to draw here only. You can draw it anywhere, but to compare this thing, I have given. So this is the result. Okay, magnetic field inside and outside the conductor. Outside the conductor, you know well. In 2 applications we have seen, but here also an application to find out magnetic field inside the conductor, in the interior of conductor. Okay, so this is all about this part. Hope you have enjoyed this thing. If you are new on this channel, please subscribe it And if you are already aware of this thing or you already know this thing, then please spread this video or share this video among many others. Okay, so keep watching. Thank you very much. All the best.